afternoon, everybody. So this is Raji from AMD, and I'm Kiriti from AMD. So we work for Mike Schmidt. He just gave you a presentation about our inference with OpenVX. So our plan today is to do a lot of hands-on and try to be able to run inference today. Just as an FYI, if you do complete inference today, we'll give you a bunch of T-shirts and a bunch of gifts. we did bring some stuff just so that you guys can run it. So the format of this tutorial we thought was, we'll first start off with explaining the whole tutorial, what each step means, what is the theory behind what we're doing, so that when we're actually typing commands, you're not lost. So that'll be the first 30 minutes where we'll just talk about what each section of the tutorial is and how the tool you're going to be working on. And then once we're done with that, we're going to go to hands-on part, where I think you might have got a sheet where you're going to log on to the Radeon cloud server. So you do not need high-speed internet. So it should work as long as you can send commands in and out and see a few images. So your internet should work. Because when we download models and stuff, the terminal which you will be on will be the one in QTS. So it's pretty, the internet should be like 100 Gbps. So it should be fine. So we'll start off with our presentation now, and Raji is going to just give like a brief about what MiVisionX Toolkit is and what it contains.
So good afternoon, everybody. I'm Raji Rautar. I am part of the MiVisionX team. I'm the lead developer and architect and working under Mike Schmidt. So our team basically does the MiVisionX toolkit, and it is available under ROCm. So what's MiVisionX is, this is actually Mike already went through this slide in his presentation, but for the tutorial reference, I'm going to go through this again. So it's a comprehensive set of computer vision and machine intelligence libraries, utilities, and some sample applications bundled into a single toolkit. So AMD has an OpenVX extension, which is AMD's implementation of OpenVX, and we deliver it as open source with MiVisionX. And we are primarily targeted at applications requiring a combination of machine learning inference and computer vision, image, and video processing. So it includes a model compiler. That's a main feature of our MiVisionX tool. And it's used for converting and optimizing a pre-trained model from one of the existing formats like FA, NNEF, and ONNX to an OpenVX backend. So after compilation, MiVisionX generates an optimized library specific to a backend. So we have architected it for different backends to run inferencing and vision pre- and post-processing modules. So why do we need an MiVisionX pre-compiled utility for inferencing? It is because we cannot deploy the heavyweight framework. When it comes to inference deployment, it is beneficial to have dedicated APIs optimized for the underlying hardware, because it is it's not heavyweight as compared to the frameworks. So all the software for MiVisionX is available under ROCm, which is AMD's platform for GPU computing and machine learning. In this tutorial, we are showing different examples which covers image classification, object detection, segmentation, and even object detection from video. And also we have hands-on training examples that allow participants to develop real-world application, including computer vision, inferencing, and visualization. The tutorial demonstrates how the OpenVX framework with neural network extension is used to deploy some sample applications. So is there any questions on on this so far?
I have one.
Can you use the mic, please?
Yep. I use CUDA and we use TensorRT. Is this TensorRT off on the AMD GPUs?
In a way.
In a way, yeah.
Yeah.
Right. So then, do you also do like when you say optimizations, do you actually do the layer fusions and all of that
Yes.
in that thing itself?
Yes.
Okay.
So the at AMD we have MI Open, which we use in MiVisionX. So the MI Open is the library which is actually used for both training and inference.
Got it.
And that's similar to TensorRT.
Okay.
So the MiVisionX is only like taking a pre-trained model and doing layer fusion and optimization, but it doesn't change the model. It
Makes
doesn't do retraining
It will
and
be
all.
optimized for the GPU itself.
Yeah.
For the hardware specifically.
Yeah.
Okay. All right. Thank you.
And I'm going to hand over to Kiriti for the rest of the presentation.
All right. Thanks, Raji. So what we're going to do in this tutorial, right? So the idea is that you all will do your own specific training or download it from some model zoo which is available open source. So the problem with open source models are they're not trained well. So when you download a model from Onyx Model Zoo or Cafe Model Zoo and you get some wrong answers, it's not because your model is running wrong. Some of those models out there do not, like you'll see in the example when we do it, they're not really trained that well, so you don't get the results out right. So the idea here as an MiVisionX is we start with a pre-trained model. So your pre-trained model could be in Cafe for us or NNEF or Onyx, and then we would use the MiVisionX model compiler and optimizer to convert it into an OpenVX graph. So while we're doing that conversion, we're going to do like layer fusion, memory optimizations, and then we're going to do quantization if you need, like if you have a model which is FP32 and you want to run FP16, so we do that. And in future, we want to support int8 option 2. So, and we also do like dynamic batch size update. Like Mike gave you an example of a server sample that we had. So for example, most of the models are not trained for different batch size. So if you have a model which batch size 1 and you want to deploy on a server, you don't want to run on every image. So you want to batch up a bunch of images and run it. So we can actually dynamically set the batch size for whatever you want, like 64 or 128. And that's a dynamic thing. So we can recompile a graph which does 64 or 128 version of it. So once you do this, so you have a graph which is pretty basic, which pretty much takes in like an input tensor and it gives you an output tensor. So most of the people get stuck with this, like, oh, I got this model, it takes an input tensor and gives you an output tensor, so you can't really make any sense of it. So you want to see what the input is and what the output is. So then you need to add some pre and post processing nodes. So for example, if you are running some kind of image through your model, so you want to be able to like crop, resize, maybe add some filter, maybe enhance it, right? So you want to do some pre-processing to the image before you actually convert it into tensor and send it to the model. And then once you get back your tensor, you want to like visualize the tensor. So they might, like different models have different kind of outputs. So if it's a classification base, you want to like, okay, you want to like get the top K, or you want to get just the top one. You want to get what is the accuracy or the confidence of the model, and you want to display it. So with the OpenVX graph, the convenience is you do not have to leave the graph structure to do all these pre and post processing nodes. So once you have your OpenVX graph, you add your pre and post processing nodes in the same graph, and then you run it. So all the memory, everything is contained in the single graph, and all you're doing for every frame is just a process graph. So it's pretty fast because the verification of the graph is done before. All you're doing now is just running the whole model. And that's the best scenario you can do because now you're running as fast as your model or your hardware allows you to do. So, and that was the point, like run optimized inference on the target hardware. All right, so So like we talked about, like there's so many frameworks out there. So people are comfortable using TensorFlow, some are comfortable using PyTorch, some just want to use Caffe. So we don't want to stop people say that, oh, you have to use this framework. So we support all the frameworks in a way that we get it through Onyx or NNEF. And you can see that NNEF and Onyx are interchangeable. So I think Gregory in like previous presentation showed where he downloaded the SqueezeNet Onyx model, converted it to NNEF. So any model out there which is Onyx, so you can convert to NNEF or NNEF to Onyx. And so Onyx has like a wide-based tools which converts like TensorFlow, Caffe to PyTorch, stuff like that. So you don't want to restrict yourself with frameworks. And once you're in this exchange format, and then we can take any of the formats we can get. The reason we want to leave the framework, like Raji explained, is you want to not come with the bulk of the framework. And usually when you run the inference with the framework on a dedicated hardware, you're not getting the best performance because the framework guys do not know what hardware you're running on. So the kernels which the framework has are not optimized. For example, if you're running on AMD hardware and you're running a framework, so it might just run the CPU version of it because it doesn't have the kernels for AMD. Right? So it's similar to like any hardware, like CUDA or any. So that's why you want to leave the bulk of the framework, come into an OpenVX graph, and just run compute, the models compute on your dedicated hardware. So Mike did talk about this tool, which is the AMD tool to analyze your data. So just in case if you do quantize, right? You want to quantize to FP16. Right now, we don't do training with MiVisionX. So there is some level of loss in accuracy when you quantize it to FP16. So if you want to measure it, like what was your loss, you could run your FP32 model, quantize it to FP16, run it again on the same bunch of images, and then you generate this graph. I mean, this whole tool will generate you the report, and you can see what classes or what labels lost their confidence, or what was the loss of quantizing. So that's one of the tools, and it's actually available. All this is available on GitHub. So I'll show you where the link is in the future slide. So this is the process that I was defining in whole. So you have pre-processing. So we're going to use OpenVX. I mean, there might be some nodes that OpenVX currently doesn't support. So you, like Mike mentioned, we have a OpenCV interop, which is also on GitHub. So you could easily call an OpenCV function as an OpenVX graph. But when you call a function from that OpenCV interop, we do not guarantee the performance on it because we never wrote them. So it's like a user-defined kernel where we import OpenCV function. So like I said, you could do like resize, warp, filter, denoise, or if you want to do something special, you could write your own user-defined node, and that is allowed in OpenVX. So you could put your own IP, create a new node, and just add it to the same graph, and it works the same way as the original OpenVX implementation. And then, like I said, the model comes through the model compiler, and that's where the model comes in. And then you could do like post-processing in the same graph, which is resize, draw, and you can do filter, denoise again if you're doing something like a segmentation model. If you get a mask, you can do that other stuff in the. So what's the prerequisites for MiVisionX? Currently, we support like Ubuntu and CentOS OSs right now. And we require ROCm supported hardware. And like there's a list of hardware listed on the website. You could just go through it. Like I didn't put it up here. It's a long list. So there's a bunch of CPUs and GPUs that we support. And for inference in particular, we need the AMD GPU or an APU because we have OpenVX implementation which runs both on CPU and GPU. And currently our inference is only on GPU. So we do require an AMD GPU or an APU to run on it. So ROCm currently is 2.4 version. So we work on any of the latest ROCm version. So when you do install ROCm on like Ubuntu or CentOS, to get MiVisionX, all you'd do is sudo apt-get MiVisionX, and that's it. You should get the latest MiVisionX on your computer. So, or if you want like the latest, like with the latest features in it, so you can just go to the GitHub, clone, build, and install. And everything is installed at OPT, ROCm, MiVisionX. And I'll show you when we log into the server what's in it. And for this tutorial, like I said, we don't have to install all the prerequisites. Everything is on the Docker. So when we load up, the Docker is already pre-installed with all the software we need. So we're just going to run the tutorial. So Mike went through this slide again. Like this is just repetition of what I said. So MiVisionX has 2 blocks. So you can see that we actually have applications on the top level where we have like classification apps, segmentation app. So we do have a version which runs on Windows, like I said, but it uses WinML. So we have a OpenVX extension, which is called a WinML extension. So when you call an OpenVX graph to do machine learning in Windows, you'll be calling an Onyx model, and that'll run through the Windows OS. So they have a way, they just take an Onyx model, ingest it, and run it with DirectML underscore underneath it. So that's how we do it in Windows. But primarily, this tutorial will talk more of the Linux side of things. So like I said, we have a bunch of apps. And then in the main MiVisionX, you have all the OpenVX, all the tools, all the utilities, like Mike described. And we also have a Loom 360. So just in case if somebody wants to do like inference on 360 videos, we do have support for it. So because it's everything in a same graph, you can run stitching and inference on the same. So it's available open source. If you want to try it out, you're free to do it. And this is what the first tutorial example will be, is an image classification. So for the first example, we'll just take SqueezeNet from the Onyx model zoo, and we'll actually convert it into something called AMD NNIR. So it's just neural net intermediate representation. The reason we do this is we don't want to like directly add all kind of work to translate every framework like Onyx, NNEF, and Caffe, and apply different optimizations for each and every framework differently. So what we want to do is bring all those formats into an intermediate representation which we understand, and which is open source, by the way. So if you want to download our GitHub and then add any feature to it or any new thing that you want, you can do it because everything is open source. And so once you get into NNIR, so that's the first step. So let me show you what it looks like. So here I have a simple model, which is, I don't know how many of you have heard about it. It's an MNIST, which is usually used to recognize numbers, right? So if that's how the model looks like, so if you see it's like a pretty small model, it has a bunch of nodes, convolution, ReLUs, and stuff. So once we use the tool to convert into AMD NNIR, it just looks like a textual format. So it just lists out what layer it is, what's the size, what's the height, width, and everything of the model. So it's pretty friendly in terms of reading it. So it also converts the weights into weights.bin. So it takes out the weights, it takes out the model description, and just clear textual format where we understand. So where we can apply different kind of optimizations on it. So did I come to step 2? Okay, yeah. So the step 2 of the part 1 where you're converting is to actually apply optimizations now. So what are the different optimizations we can apply is what we can do is we can update the batch size. Like I said, you want to run it on a server use case. You have some model which is batch size of 1. You want to update it to batch size of 64, 128, 256. You can do that. And there are some models, like for example, convolution bias ReLU, or some other nodes which follow together. So we can actually fuse those operations and call one node instead of calling multiple nodes. So all you would have to do is call this command, which is NNIR update fuse. So we'll go through the NNIR graph and fuse those nodes which we can run more optimized. So that's more of the fusion. And then, like I said, we can also quantize to FP16. So the next step is converting this optimized NNIR to OpenVX code, the C code, right? So you're just going to call this Python parser. You're just going to give your input NNIR, and you're going to give you a folder which is an output code generator, exactly like Access Communication. They drew all this graph and just generated the graph, OpenVX code. The same way we just generate an OpenVX code. And for that model, like the MNIST, this was the OpenVX code generated. So it's all there, so it'll generate the same exact way Access guys generated. It's just the code, and then you just add it to your graph, and then you run. So that's the sample one, like in high level. And like I said, you could add, now that you have your model in an OpenVX graph, you want to do pre-processing, post-processing, go ahead and add whatever you want to it manually and just run it. So the first part of the tutorial, which I will do more like manual stuff, like do all these steps one after the other and just do like slowly and try to add it by yourself, because some people prefer that. And Raji has another method, which is the second part of the tutorial, where all you'll just type is one command and does all this at once and just gives you a library that you can call through the application, right? So we just wanted to do both. So we want to show you that you can manually do everything one by one, or just call one command and just be done with it. So, and then if everything goes well today, we will just see an output which will come up on your screen, and you should be able to see something. So this tutorial has an unified application. So basically, when you generate this OpenVX code, you're just going to compile it with the application. The application just gives you the visualization of your input and output so that you can visualize as an example. It's just sample app, so feel free to take it, use it, or contribute back with more features to us. We are always open for that. So the second example, we'll be doing like the same similar way, but not classification. We'll just run object detection model. So for this case, we'll just download an YOLO v2 Onyx model, Cafe model, and just run it. And if we do that, then we'll run another NNEF model from NNEF model zoo, just to all different formats we have. So what we'll do is we'll start with example 1 with mine, and then we'll switch to example 4, which is Raji. And then if some people are fast, some people are like be done with example 1 when we are just talking about it, feel free to go ahead and just do the example 2 and 3. And then I also have an example 4 if you're really good. We'll give you a tumbler for it. So Raji will explain the second part of the tutorial, which was the deployment package, where you're just going to type one command and it'll do all the manual stuff that I just explained.
So I'm going to talk about this Inference Deployment API. This is relatively new, and we just got it working last week for this tutorial. And the reason why I started working on this is because when we partnered with people and they had problem following the steps, which converts from different model to NNIR, then NNIR update, and NNIR to OpenVX, and they get lost in all this different step, and once you miss one step, then it doesn't work. So this is actually like this utility, which I call an MiVisionX Inference Deployment API. So it started with creating some APIs, which is not specific to OpenVX. It's just generic API, but on the back end, it uses OpenVX. So there is, it's architected to support different backends. So we want to support OpenCL underneath with ROCm, and we also want to support OpenCL with HIP, and we want to support WinML, and in future we might support a dedicated hardware underneath. So all of that, we want to use the same API to deploy the inference. We don't want to change the code for each and every backend. So that is another intention behind developing this inference deployment API. It's a two-stage process. First is you compile the model. So it does take a pre-trained model in one of the format, and then it converts to, you specify certain options to do like model optimization, backend, wish model, and then we will be showing that in the tutorial in detail. And it once you compile it, it generates a deployment library, which is right now it only works for Linux, but in future we will make it generate a deployment library which is specific to Windows and vice versa, like etc. And it have the weights of the model and some header file and CPP file to run the inference engine. And also, most of the inference application, when you want to generate, want to develop an application, it requires some extra stuff added for pre-processing and post-processing. So we actually generate some kind of module for doing most common pre and post-processing like argmax and bounding box, object detection, etc. So I thought it's better to show in a block diagram what is this inference deployment library, the stages look like. So we start with a pre-trained neural network model, and then we convert to NNIR. Then we optimize the model in that intermediate representation because we just want to deal with one representation when it comes to optimization. And then this particular utility, which is called MV compile, it is including all of the stuff in that dotted box. So it compiles and generates a C library, which is actually a package which has a library weights and some sample application. And the application uses that package to actually do develop the real world inference application. So this is some detail about the options, command line options. Again, we are going to go through these options when we do the tutorial, how to specify that. So basically, it takes a model, pre-trained model, and it says where do you want to install the library, input dimension of the model, the backend where you want to generate the library, and then it also takes fuse operations, quantization mode, etc. And then after you compile, you deploy the compile model with optional pre and post processing functions. So again, in the sample, we will be showing how to use that in the object detection with a video sample. These are some of the functions in the deployment API. So this is actually generic functions. There is nothing which is connected to OpenVX in it, but in the back end we will have all the OpenVX stuff in the handle. So basically you call a initialize deployment with your install folder where you generate the library. What it does is it actually goes through the NNIR and learns about the model when you do the initialize deployment. So after that, you can query the inference. So basically, when you have a model, you don't know what is the input dimension until you go and segment the model and go through each layers. So after you do that, you can query the inference. The application can query the inference for the number of inputs, number of outputs, and the dimensions of that. So this is needed. So because when you actually load an image as the input, you want to know like what's the size the model accepts it. And this also, the API also has the option to have a pre-process callback. It also have post-process callback, but I haven't put that in here. This is all the main functions. So what it allows is the set pre-process callback function. It gives you the application when you create the inference can set that callback function. And while in the create inference session part of the code, after it calls that function to add your pre-process nodes into it. So it's basically like adding the pre-processing nodes into the same graph. So you don't want to like unnecessarily copy your data back and forth. And also it has set input data from memory or file. So this particular function has the option to actually, it creates a virtual memory in the VX, like create virtual tensor function. So basically, when you set the input from a memory file, it does a swap handle. It doesn't actually copy the memory. So the application can create the tensor memory and copy the data and call a swap handle through this API, so it doesn't do extra copies. So after that, it can call run inference, which is basically calls process graph on the back end, and it can be called for as many frames as you need, like in a loop. And for each of the run inference, you can call get output, which is the output of the inference with the pre-processing. So, and MV shutdown function, which is the which releases all the resources for the inference and releases the OpenVX resources, etc. So this is actually like explaining what is the sample which I will be going through in this tutorial section. Again, this is actually a summary. We will be going through each and every step in the tutorial. So in this sample, what we are showing is how to add pre-processing node. In this case, we are having a video decoder node. We have a AMD video decoder node implemented as an OpenVX user-defined node. And also we have the inference in a graph, so running both of these things together. And also it shows the use of MiVisionX utility, the MV compile, which I explained before, which is used to compile a pre-trained model into a specific backend. So I already said that it has to add pre-processing nodes, and also it demonstrates how to build an application which does object detection using, in this case we are taking a YOLO V2 model. And also we have, once you get it running for one video stream with object detection, by simply compiling the model for a batch size of 4, we will put that deployed library into with the 4 video streams and show how it scales up for 4 video running object detection for everything together in the same graph. So this one is actually showing the block diagram. I thought it is easier to understand from the block diagram than the other one. So it takes a YOLO V2 pre-trained model, then goes through the MV compile utility, which generates the deployment library and the weights of the model and some CPP files and all. And then the application, which is called MV object detect example, it calls the initialized deployment, which basically like loads the library, sets all the function pointers, etc., to run the inference. And then it calls create inference, which basically creates the VX graph, the OpenVX graph context. It does a verify graph of all the inference. And then you can call run inference, and in this case, it loops through all the video, the frames in the video. And what the run inference is doing is calling VX process graph. And then after it is done, it releases all the resources. This is also same using the steps of running the sample. We will be going through this in detail, so I'm not going to go through this right now. So any questions on this? So I was just going to show the output. This is actually running 4 video streams, decoding, and the decoded output goes into a single tensor with a batch size of 4, and then we do the inference on that, and then do some visualization using OpenCV, which draws the bounding box around the objects. These are the links for our tutorial, which we'll be doing in a bit.
So if you guys want to open up the tutorial part 1 GitHub page, that's where we're going to go through all the
should break and then do the tutorial.
So we can take a coffee break and come back refreshed and then start coding.
Again, whoever does the tutorial and finishes it, we will be giving freebies.
Yeah. We want to see how many of you compile OpenVX today.